3 days after you buy a loaf of bread, it turns hard and crumbly. It feels bone dry to the touch. The logical assumption is that the water inside has evaporated into the surrounding air. We can test that logic by removing the air entirely. If you seal a fresh slice inside an airtight bag where no moisture can escape, the environment is effectively frozen. 48 hours later, the result is the same. Despite zero exposure to the outside air, the bread still hardens into a dense, crumbly brick. Placing that sealed bag on a scale reveals the data anomaly. The mass is identical to the day it was packed. Not a single gram of water was lost to evaporation. The hardening of the crumb is not dehydration. It is a physical, reversible molecular rearrangement. This phase change is known as starch retrogradation. Because we mistake this shift for drying out, our instinct is to move the bread to the refrigerator, a habit that inadvertently targets the specific conditions that make bread go stale. To understand why the cold is so counterproductive, we have to look at the microscopic architecture of the loaf, starting with raw wheat flour. Raw starch exists as millions of tiny granules, tightly wound, microscopic crystalline bundles of sugar molecules. When you add water and heat in an oven, these tight bundles undergo a radical transformation. Somewhere between 60 and 70 degrees Celsius, the granules drink in the surrounding water and swell, causing their neat crystalline order to fail. The starch unwinds into a loose, tangled mesh. This disorganized network traps the water molecules within its tangles, holding them in place. This waterlogged state is scientifically called gelatinization. Every soft, springy crumb you've ever eaten is essentially starch in this swollen, disordered state, cradling water inside its structure. But freshness is a temporary state of thermal disorder. Thermodynamics dictates that over time, these molecules will attempt to return to a state of order. The reversal begins the exact moment the loaf leaves the oven and begins to cool on the counter. As temperature drops, the polymers seek a lower energy state and spontaneously begin realigning into crystals. This realignment is governed by two distinct starch molecules, amylose, which forms a simple straight chain, and amylopectin, which is highly branched and sprawling. Amylose is linear and easy to organize. These chains line up side by side like a handful of pencils. This is why a loaf feels noticeably firmer just 12 hours later. The rapid crystallization of amylose creates that initial overnight stiffening. Amylopectin is much slower. Its bushy, branched structure makes it clumsy, taking days rather than hours to settle into a crystalline form. This slow, relentless grind is what turns day-old bread into a doorstop by the end of the week. As these crystals tighten, they physically evict the water that was nestled in the gel, squeezing the moisture out of the starch structure. This water hasn't left the loaf, it has simply migrated into the surrounding gluten network, causing the interior structure to stiffen and firm. Staling is an internal tug-of-war over a fixed pool of water, where hardening starch shifts moisture to places where it can no longer keep the crumb soft. Since staling is driven by these molecular clocks, we can control the speed of the hardening by changing the external temperature. Most kitchen logic assumes that colder temperatures slow down decay, a rule holding true for milk, for raw meat, and for vegetables. Retrogradation, however, does not follow a linear path. For starch to crystallize, it needs enough thermal energy for molecules to shuffle into position, but a temperature cool enough to allow them to lock into place. These two requirements create a kinetic sweet spot, a temperature range where the rate of crystallization reaches its absolute peak. This peak happens precisely between 0 and 4 degrees Celsius. That specific range is the standard operating temperature of a home refrigerator. Stashing bread in the fridge to keep it fresh actually places it in the one environment where amylopectin crystallizes at its maximum possible speed. Far from preserving the bread, the refrigerator acts as an accelerator for the very architectural collapse you are trying to avoid. If mild cold is the catalyst for staling, it raises the question of whether bread should ever be chilled. The solution is to bypass the danger zone entirely by dropping the temperature as quickly as possible. At -18 degrees Celsius, the temperature of a home freezer, the rate of crystallization effectively drops to 0. In this deep freeze, the water locks into ice and molecular movement stops. The starch chains simply cannot move to line up. The freezer serves as a permanent pause button for the staling process, locking the bread in whatever state it was in when it was first frozen. To handle bread that has already crystallized, we have to look to the opposite side of the thermal curve. Because retrogradation is a physical reorganization and not a chemical decay, the process is reversible. Applying heat above 60 degrees Celsius melts those starch crystals apart, forcing the starch to reabsorb the water and return to the soft, disorganized state it had when it first left the oven. Stale bread is a reversible crystalline structure. Once you account for the movement of the starch and water, storing and reviving a loaf becomes a predictable exercise in thermal control, when you can pause or rewind whenever you need.